Sağlık diye niyetlerine obsession class says so those. Okay, we can start that. So last time we went through all kinds of classification of systems. Okay. Remember where we are. Single input, single output. Linear devices. Tiny value. And relaxed. That's what we see. These devices we can find we went through these things, right? Three models that you have learned in your undergraduate is transfer function, state space, this has signal and system core circuits, state space they call it, and impulse systems. These are the three models that we use. This typically, the most important one is transfer function. Okay, the state space model, I'm not going to be using it here, but I'm going to cover for you so that you can understand why. Because when you start working, you have to deal with the state space model. In fact, I strongly recommend those of you that are concerned about your jobs and things, you have to have a skill. Okay, I don't know how to explain this thing to you. Nobody hires you if you don't have a skill. So in order, if you're concerned about your skill, go through E501, even audit it so that you can familiarize yourself with the state space model carefully, properly, because you have to work with it. Okay? Various industry that you go. A state space is used in MIMO, multi-input, multi-output. You move from frequency domain to time domain. Okay? But the single input, single output, which is essentially your undergraduate, okay? Everything that you have seen is a single input, single. It is transfer function does beautiful thing job. Moreover, we have two things in a frequency domain that gives amazing power to engineers. One is a Nyquist, the other one is Bode. We have these two things. When we design filter, when we design anything, these two things that we have, and you will see it in these course. Okay. With the transfer function, remember that ODE is like this. We will discuss this thing. With a constant coefficient. Everything that you model in a seesaw case end up in an ODE. This is the ODE. Okay? Relax means initial condition is 0. My hope is you understand at this time if initial condition is non-zero, you cannot have a transfer function. Are we good in that one? Complete. So as soon as you talk about transfer function, we're talking about very specific case that the device doesn't have any energy stored. Initial condition is 0. Okay. Then you can take a Laplace transform, of course, of this. When you take a Laplace transform, something like this, the beauty of relaxedness is when you have a derivative of a signal, Laplace of it, say nth derivative of a signal would be s to the n times the Laplace of y. Okay? There's no initial condition pops up. So you get something like this as soon as you take the Laplace transform. This is because of this. There's no initial condition involved. Okay, and then you put this thing, and finally you get this. This is your transfer function. Polynomial divided by polynomial. Okay, so transfer function for you becomes polynomial divided by polynomial. Has a name. When you have polynomial divided by polynomial, it's called rational function. Okay, just make sure you understand that buzzword answer. Poly divided by poly, it's called rational. Here it is. Remember what I told you, causality versus non-causality? The power power of numerator has to be less than or equal to the power of denominator if your system is causal. Okay? If your system is causal, n has to be less than or equal n. If n is greater than n, you are a non-causal device. And we don't deal with non-causal device. Is that clear? How many of you have built differentiator? Anybody in whatever classes that you have? A differentiator?
A differentiating amplifier? I'm pretty sure at some point we had built one in 311.
So the transfer function of differentiator is what? Input goes, the output is y dot. What's the transfer function? As soon as you if somebody says a differentiator, that means it's a device. You go u as an input. The output is y equal to of u dot. Make sense? What's the transfer function for this? Y equal to u dot, ODE. You just learned this. So it would be y of s equal s us. Do you see it? Y of s equal s us. Transfer function is s. It's a non-causal. When somebody decided to teach you differentiator, has to start from here. It's non-causal. I cannot build this. I have to convert it to some approximation of the causal phase. Then I can build it. Okay? Using a pound element, etc., or variety. This is an actual function. You can think about it as divided by 1, or divided by 4. Make sense? But it's not causal. You have to convert them to causal. Maybe I can put in denominator something like an epsilon, some small times s plus 1, some approximation of differentiator. And building differentiator is complicated because they're highly sensitive to noise, etc., etc. You have to, there are many things you have to work it out, beyond the scope of this course to even build a differentiator. Okay? But anyway, differentiator is non-causal. So the causality requires the power of numerator to be less than equal to the power of denominator. Is that clear for all of you? So the roots of denominator is called poles of the system, which you are all familiar. Right? The roots of the numerator is called zeros of the system. So essentially, the transfer function becomes bunch of poles and bunch of zeros. Okay? Actually, if in an engineering term of zero is transmission zero. When you work, you talk to the engineer, they don't say zero, they say transmission zero. And there's a reason for it when they say transmission zero. Because if you have a zero at some frequency here, whatever it is, if you excite your device at the same frequency, it gets blocked. You see zero response, or zero cancellation occurs. Okay? That's the reason they say transmission zero. Okay? So learn those buzzword things. That the learning engineering term is the most important thing because always they have more meaning to it. Okay? So transmission zero is just block the frequency. If I have a zero at certain frequency, if I excite the system with some input at that frequency, it gets blocked. Therefore, transmission zero. No transmission. Okay. When you deal with a transfer function, okay, when you deal with, let me see that I have one example. So in this class, during the lecture, we also work, and I ask you, for example, let me do this before time delay. Time delay. Think about the delay device. Think about the delay device. So, delay device or delay filter. Have you guys seen any delay filter or not? In any courses? is a device. Again, always put the system here, put a system. UT goes here, and you get the YT, right? YT is a delay of this. Exercise for you. This device is linear. Satisfy superposition law. Verify it. Put the U1, the U2, weighted sum, see whether it's same. Is that clear? It's a timing value. So as soon as you see a device, you look at it, and then it's an LTI device. If it is LTI, you say it has a transfer function. Okay, has a transfer function. Take the Laplace from both sides. Okay? So this is your time delay. Take a Laplace from both sides. Take a Laplace, transfer function is e to the minus TS. That's the transfer function of delay. Okay? Now, again, here comes engineering. I have to, somebody says, build the delay filter with certain delay time, 0.5 second, whatever it is. How do I build e to the minus TS? Again, there are all kinds of these are sophisticated things that you should have learned in some, I don't know, some classes in your undergraduate. So you have to come up, if you want to build this, you have to come up with a rational function that approximates this guy. Rational function, and as soon as you get the rational function that approximates this guy, you're good to go. You can build that rational function. Make sense? Now, to come up with a rational function that approximates this, there are all kinds of technique things, because some engineer does better approximation than the other. Therefore, you have a better device versus the other. Does that make sense? Okay. So we familiarize ourselves with delay things. Here's, I have done some approximation here for you to see. They have all kind of name. I don't want to go through this thing. Sculptors have the approximation. There are all kind of other approximation, okay? But I have done some stuff here, okay? Maybe you can use this one. Go to your lab and build. Okay? So you can say it. There are many different kind of approximations. So some of them you might note it here. Okay, can you guys do this? Transfer function for this secret, let's say 4 minutes. Good. 4 minutes. Output is V, input is I. It says find the transfer function V over I.
Which I is the output?
At this, it says V is the output, I is input. V divided by I. Obviously, Y divided by U, which that's what he's asking. which is transfer function. Transfer function, which is equal output divided by input. You look at this. Output is V, input is I. Those are done. This is, you know, I was involved in us with some of the Bay Area hiring things. When they want to hire you, you have 2 or 3 hours technical interview. 5 minutes. Can you do this? Can you do that? And they really measure you whether you really have a skill or just prepare yourself. It's called a skill. Okay? All right. This is a trivial one, right? Like a crucial one. This I equals somehow this guy with the good down. That's what it is. When you got the crucial one, then you can take a derivative of this.
It's hot, that's why we have it like that.
I'll get the
Listen.
AC turned on.
Alright, thank you.
Yeah. I is equal, just application to this rule. I equal IR and IL, plus IC, put them all of them together, it's just what it is. Everybody this? Which comes up with this. Gives it a this antibody, but taking a derivative of it. Okay. You have to convert this into ODE. You have to take a derivative of it. Gives rid of this guy. Okay? My hope is that you all don't know how to take a derivative of this with respect to t, which is the upper limit of this angle. If you don't know, just talk to me later. So if you take the derivative, it becomes this, your ODE. Take a Laplace, you're done. Yeah, with this. Make sure you know how to take a derivative of this. You're taking derivative with respect to t from article, the upper limit is t. You remember it in calculus, Lifshitz rule. Lifshitz rule, sorry. Okay? Good. Then you say, hey, I'm going to take a Laplace. That's the transfer function. This is what we have. This is the transfer function of that suit. Okay? Make sure you know, this is the most simplest possible circuit ever. You have to look at it, you know. You know what, when you work with engineering, even they don't write those equations. They look at the circuit, they know transfer function. In their head is a body plot shows up. Okay? Literally, when you work with them, you have a circuit shown to the person, and the person in his head already body plot is there. And see, body plot tells you this circuit, how does it behave? Okay. So transfer function moves us from time domain to frequency domain. As I said, frequency domain, one of the first elementary part of the frequency domain is I can have a series connection. Various maybe, but you put two devices in series. Okay, transfer function for addition of these two. For example, that's a series connection. It's parallel connection. It's other. This is a series. So instead of this, trivially I can do this. Okay? Parallel. You can put a parallel. Oh, transfer function is added. Feedback. So you have a series connection, parallel connection, and a feedback connection. Let's look at the feedback. Suppose I put them stuff here. Write your equation. E of S is equal to R of S minus y goes through this side, A of S, y is GS ds. GS times ES, you have this equation. You find the relationship between ES and RS from here. It's algebraic. It's 1 over 1 plus GK. Y over R over G divided by 1 plus G. I don't know why the zoom doesn't work now. Stop me with this out of this. Unfortunately, Zoom doesn't work in this stuff now. Okay? You see. Make sense? So with the transit, so what does this tell you? This tells you in a really complicated topology that have various devices with feedback loop, you know, various loop and series, and I can look at it and just define transfer function overall topology. Make sense? That's the first thing. So going to the frequency domain, obvious trivial thing allows us to do all these sort of things. And then, as we'll see in this course, it can provide you ability to do amazing stuff in frequency domain. Okay. All right. Now let's look at Let's look at some other model. Okay, so this is transfer function. Hopefully you do a bunch of homework, etc. So we are good. So remember that we have a system is driven by input multi-dimensional maybe, whatever it is, or in this class called a simple, and the data.
It's up the screen a little bit.
Yeah. Okay, we work with this. What the data is, data. Data is called state, right? We have discussed this thing many times. And the standard notation for it is X and T naught. So, like if you have ODE of order of n, how many initial conditions do you need? A finite number of initial conditions. So this would be always finite number. So that's why you need n of. Okay? And time t naught, which is called state of a system. What is a state space model is look at the evolution and changes of the state as the time goes by. Look at the evolution of the state. How do I look at the evolution of state? Look at the change of the state. Change means what? Velocity. So they come up with this thing. They don't assume system is relaxed. No relaxed assumption. It's a very general model. They come change in a state called AX plus BU as we have seen it, and Y will be equals CX. This becomes the state model. Okay? Let's look at this. This is what you have seen in one of your classes. X is a vector. General in dimension. A is n by n matrix. Okay, times this. B for your class single input, so it would be n by 1. But if the input is multiple input, it would be, suppose you have n input channel to device, this would be n by n. Make sense? Output is the one that you're interested in. You put the sensor and measure something. Okay? So if you have one output, C would be what? A row vector of dimension 1 by n times x. So the model for engineer is A to C. That's what they call it. Okay? And again, from engineering perspective, this is the when you work, B represents really the location of actuators, where the actuators are located. C represents really the location of sensor. What in a state did you measure? Okay. So when you go to MIMO, you cannot really work on the frequency. You have to go back to the time domain. There is no multi-input, multi-output transfer function. Everybody goes to the state space, and then you go here. And you have to learn this model. It is extremely important to understand the state space model, and that's BE 501. Educate yourself what it is, because there's so many things about this model. Value state, controllability, observability, detectability. There are all kinds of things. All kinds of things, okay? So I just touch upon this and I tell you how to go from ODE, okay? Let's say the space model. So now we went through this. Sorry, this Zoom is really dramatic here. Okay, we have an ODE or transfer function. Going between these two is trivial, correct? Going between these two is trivial. If somebody gives you transfer function, say, hey, give me ODE, this ODE, take the transfer function, relax assumption. Now I am given an ODE, like think about that circuit that you just did. I'm asking what is the state space model for this? Okay. How do you get the state space model? So what we want how to get the state space model from ODE. Remember the ODE that we have in this course, summation of AI, YI, N of them is equal summation of M of EI, UI. UI means ice derivative of U, YI means ice derivative of Y. Is that clear? Okay. So we want to go from here to here. We do it two steps. The first step would be, let's get a special case. This one is a standard one, but I didn't put any derivative of U here. I just put U. Let's learn this first. Okay. And then we go to the general. So the key question is, if somebody's written ODE like this, what is the transfer function for this guy, for example? Anyone? Transfer function? 1 divided by polynomial AISI, summation I goes from 0 to n. Okay, just look at this. Okay? This device doesn't have any zetas. Has n poles. 1 divided by an Sn plus an minus 1 Sn minus 1, blah, 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 blah. When you look at this, obviously transfer function will have screams at you. Okay? Choice of a state. Let's start with, let's say in U ODE you want to solve this guy. It says, give me the U and give me the initial condition. Let's see what initial condition you will need for this guy. That's the choice of a state. I need Y at time 0. I need n initial condition. This is a ODE order n, you need n initial condition. You need to know Y at the time that you start, Y dot at the time that you start, Y double dot at the time you start, Y true, just up to Y, okay? Is that clear? This is a set of data that it's called data, right? Now label that, because the state is called X. Label the first one, the Y as X1. Label this guy as X2. All of them, okay? This is the state of your system. Okay? So this choice of a state now made. Then you have to do algebra. Algebra means what? I have made the state, I have made the choice of the state. Take a derivative of it and see whether you can convert it to external variables. Okay? So let's start up. Choice is made. Let's take a derivative. Derivative of x1 is xy dot. But y dot equal x2, correct? This is nice. Derivative of x2 dot is y double dot. Y double dot equal x3, correct? Right? Derivative of x3 is y triple dot, we just go on. You can go on up to the last one, which is x n dot equal n's derivative of y. Is that clear? Okay. Now make an observation. You have your ODE. You remember what is the ODE? This was your ODE. an, derivative of y to the power of n, blah, blah. If you look at this, you can write your ODE as like this. Yn is x n dot, so it's the base of x n dot. A and x n dot equal u minus this. Okay? So finally, my x n dot would be this. Then I'm done. Then I have to put in the matrix form. So the key question is, when you take a derivative, it has to come a relationship of the other state, derivative has to be combination of other state and input, nothing else. And I'm done because when I take a derivative, it's a state of others. And for this guy, I found a combination of other state and input. Is that clear? Combination of other state. If you want to take a note of this, do this. Choice of a state. And not after, this is this, so this can go here. Yeah. Put it in a matrix form. This is what it is. This is your main. I wrote that algebra because x1 will be what? This times this means x2. Super diagonal into this is 1. Bottom row is this. E is this. Okay, first let's look at the A. This is your A. And X. What is the B? It's unfortunately small things. This is your B plus B times U. Okay. The output was x1. So obviously your C would be 1, 0, 0, 0. Picks up the first element of the X. Is that clear? That's the ABC of that device that we worked about. Choice of a state, take a derivative of it, and make sure the derivative has to be linear combination of other state and input. That's the key. Yeah? Then you are good to go. Let's go to the general. General case gets a little bit complicated because we have to involve derivative of input as well. This is general form, right? Again, you need n data. It's the ODL order of magnitude. The first thing, how many data do I need? N. Choice of a state would be those data. Okay? I'm going to show you very shortly that the choice of a state is non-unique. And that's really what engineers they use. They need to change the model based on a variety of reasons for the design, etc., etc. Okay? So you have this. The choice of a state and choice of a state, I chose this guy. This is the choice of a state. Obviously, from here, you can get the y equal this choice of a state. As soon as you have a choice of a state, the rest is algebra. Okay? Obviously, I have to take a derivative of the choice of a state and see whether I can convert them to linear combination of other state and input and put them in a matrix, and I'm done. Okay? The key question is choice of a state. As soon as you make the choice of a state, the rest would be algebra. When you want to write it down, put your stop me, make sure you're completely done with your writing. In the general form, always you can use this choice of a state based on the coefficient of ODE that you have. The rest follows. And take a picture as well. This. Then I have to take a derivative of this guy and do the algebra. That's all there is to it. and manipulate this stuff. And that's what I'm gonna do. I'll wait for them to finish it up. Good. Okay. The rest is a linear algebra. I start taking derivative of this stuff. You see here. Start taking derivative. What's up? You just do the algebra. Everything is straightforward from now on. You have to do the algebra and figure it out to convert the right hand side linear combination of other state and that's what we do. Everything here is really good because the linear combination of input and state, x and dot. I have to put a question mark, I have to work it out and figure it out. Okay? A little bit work has to be done. Up to here, I'm good to go. For x and dot. I have to do some stuff. Oh, you want to make it? Okay. Good. This is a derivative. X and dot is an issue. So I'm going to just do this algebra. This is just algebra, really. Finally, I got my x and dot equal this. After all this algebra, this is your x and dot. Then come back and put in a minute. So there we go. Let's start with the A. The A of a system looks like this. You have all the A's, the coefficient that are for the outputs here, all of them normalized by AN. With the one super diagonal into the matrix A. Okay. Your V matrix is this. That was A, that's your B. And that's, let me just add one more thing here. The more general one of the model, I'll come back to that later. In some cases, you might have a feature in G that you refer to as feature. So you have like a U also shows up. Okay. Not for a strictly proper system. Strictly proper system, this doesn't exist. But anyway, this is your C matrix, that's your P. So yes, from ODE we can write a state space model. Okay, a state space model is not unique. So when you give the engineers some model, whatever they want to do, suppose they want to filter design, suppose they want to do signal processing, suppose they want to do control, etc., etc. They have to massage the model. They have to come up with a model that gives them some better understanding for the, it's all about the design. They refer to that clearly, a special model as a canonical form. There are 24 of them, etc. They massage this stuff to get a model that gives you understanding of the structure of the product so they can work. Okay. So for you guys, I'm just going to say the following. The state space is non-unique. Non-unique. If you start with a state space model, okay, that's what they do. So you choose a state called things you did, give me a model. I can always change this model to some other A, B, C, D. Or choose a new state. Okay? X is an n-dimensional vector. X hat is a new state. T is an n by 10 invertible matrix. This is called a state transformation. The data doesn't get lost. If somebody gives you X, you can find X hat. Somebody gives you X hat, you can find X. So you are not losing any data in this transformation. That's the key. It's a one-to-one mapping. You have an X, some state with certain choice gives you X. I can go to X hat without loss of anything. Okay? Now, these are non-singular environment. That's what they do. Then you start saying, okay, now I'm gonna look at the evolution of this guy. Take a derivative. Okay, derivative is equal to t times x star. X star equal to x plus bu. And instead of x, we can put t inverse, multiply by t inverse from this side, t inverse of x. This becomes t a t inverse x hat. This becomes t b times u. Your new c will be c t inverse, and the d remains. Guess what? I didn't change the relationship between input and output. But actually, my a mu is this guy. My b mu is this guy. My c mu is this guy. Okay? Every design that you do requires this at the first step to go to the right coordinate they call it. Right, going to see this. If I want to do the field design, I have to do this. And if I want to do any design, it shows you certain things and has all kind of a names, contributing canonical form, observability canonical form. It's just so many of them. Okay? So you should be aware that the state space model is not unique. Obviously, you can do the state transformation, as I said, nothing changes, no data got lost. Okay? These two are equivalent. You know one, you know the other. You know the other, you know this one. Okay? But what it does, it changes the ABCD that you as a designer you want to work with. Okay? Which at this time you are not familiar with the design, so I cannot go further, but it's a very crucial step. It's a very crucial step. I can tell you with one thing. Okay? Long time ago, when I was about to graduate, etc., I create one special of this guy. It's called SCB. Okay? One special one. It's called SCB. It's an architecture of a dynamical system. When you go to SCB, you see all kind of things, what the signal does, where it's gonna go, how it gets amplified, etc. It's complicated. SCB became a course at UW long time ago. Now SCB is a course in many schools actually in Europe. You have to understand this because that's needed. If you are a designer, that's what you need to do. You have to see this. Like, example that I can take a picture of a building and say, oh, this is a building. Okay? Or I can give you architectural planning. The human goes in there, how does it go? How does it move? Goes from where to where and then what to what? Devices have internal picture. What's happening to signal when it goes there? Okay? What is happening to it? When you design, you change the architecture. It's an internal architecture of device. Is that clear? Someone understand? It is so significant to understand this that we do have different ABCD and we work based on what we are supposed to do. Am I doing filter design? Okay. Am I doing adaptation for some dynamical system? Okay. So depends on what you do. Okay. So one other things that I'm gonna do in steady space, but not now, in the future, because I have to get back to our thrust of this course, which is transfer function frequency domain. The key question is this. If in a steady space model, I'm gonna cover this thing for you. If somebody gives you input and a state at initial time, in other words, if I give you of t and the state at time t now, how to find the state of the system. Okay? Solution to this. We will cover that one at some point, just for you guys to know. But a strong advice to you, learn steady space model to some extent, which is E501, somehow add it, whatever it is, if you can. Okay? Which is possibly our next semester. Next time.
Yeah.